I'm gonna talk about kind of my general work and then focus more on the FPGA side of things. The work that I talk today is from UCSC and MIT before I joined Nvidia, and feel free to ask questions in the middle. So we are seeing that the network traffic is increasing, and the main point is the number of internet users worldwide are just increasing rapidly, almost linearly. And then with the services they want to use, like cloud, videos, and so on, we are seeing exponential growth in the global internet traffic. And then the question is, okay, this is how the internet traffic is increasing. How is the technologies coming along? And then the point is the good news on the x-axis I'm showing you here, and over the y-axis we have a log scale. We see that the wire speed per one line, we can actually do exponential growth, which is nice. Newer technologies are coming for networking. But unfortunately, when we look at the compute capabilities, how many transistors you can buy for $10, it's plateauing already. Kind of many call it the end of the Moore's law, that around 2015 or so, things started to become slower. And even more important is the frequency part, that because the Powerball in early 2000 and the Denard scaling, we couldn't increase the frequency of our transistors with the same power budget. So these together mean that from a single core, the performance I can get is less than before. So how could we come up? So now that just by technology, I'm not getting an exponential growth on the compute while I get on the networking, the question is, how can we cope with this scenario? The workaround was to use customized hardware. The idea is that if I make my silicon specific for my application, I can make it more efficient compute-wise, and then I can keep up with the demand. And then it has order of the magnitude improvement in both performance and energy efficiency, which together are shown as the total cost of ownership. And for example, the money that data centers have to spend to provide a service for the cloud users. And then initial examples of customization was, for example, IntelliXion in Facebook, that they provided some accelerators in the Intel CPU, and they were able to do their job. And obviously, you know about GPUs for machine learning jobs. And then some companies went even further to make it more customized. For example, you know about Microsoft Catalog potentially that has the FPGA that are reprogrammable, and they have faster turnaround, or like Google VCU, the video coding unit. Actually, I was at Google when this was starting. And then we did some elaboration that actually it makes sense to go all the way ASIC if you want to redo the exact same thing for like a year and a half. And then it becomes cheaper at the scale, so we need high scale. And then the customized hardware is everywhere in the cloud, that users talk to the base stations or to their ISPs. On the other end, we have the data centers that they use customized hardware. And then even in the backbone internet, you have network middleboxes that does processing like firewalls or checking the internet traffic. And then previously, most of them were done on general purpose hardware. For example, we did video search on CPUs, we did firewall on CPUs, or we used DSPs in the base stations for signal processing. But if we look at what are being used today, as we talked about data centers, we already have both FPGAs and ASICs. For firewalls, for middleboxes, again, we've seen both. And then for signal processing, we are even seeing FPGAs already are common in the base stations and antennas. And then even there are something that for 5G, there might be ASICs. The tricky part is this, the customized hardware requires converting part of the networking application that we are doing to hardware. It's not just software anymore. So here I was thinking that you are telling me that the networking software developers are either becoming hardware developers to make it to be hardware or closely collaborating with them. So what's the challenge of this hardware? Okay, let's just do this. The tricky part is co-design takes time and requires a different skill set. Overall, we have functionality and we want to just make it to be hardware, to do a logic design. That's on paper. First of all, it has a very unique and different skill set. Writing Verilog is not writing C. Even if you do HLS, you have to be very aware of the hardware and how you can use the resources. Another thing is there is a feedback cycle that for co-design, that there is the hardware software interface simulation and going back and forth. And this cycle takes a very long time. Why? Because this logic design part takes days. The point is the logic design would give you a hardware description and you give it to EDA tools that they do synthesis, do the optimization for you, some placement, where to put it on a FPGA or ASIC and routing among them. But, and then it gives kind of the bit stream for FPGA or the map for ASIC. The problem is, even though these EDA tools are automatic, it takes hours per run. And then timing or resources constraint may fail, you have to update and repeat and do this back and forth, back and forth. So even when you have a hardware that seems to be working in simulation, it takes a really long time to make it happen. And then this was, for example, for FPGA tool. And then now if you want to manufacture an ASIC, you have to first make the FPGA as a prototype, then do the ASIC, you have to do the foundry. That overall can take 2 to 3 years. And that means a very high upfront cost and development cost and time that you have to spend. It was interesting that, for example, the MSR Microsoft research paper on the NIC that they're using FPGA, they mentioned in the paper, one of the most important things that they realized was to have the hardware and software teams work together in one group. That was the important thing for them to do. So I had a question in the heart of kind of my research work that, is there a systematic way to lower the barrier to entry to use customized hardware? Should it be always like this? How can we reduce the development time and cost? So my research, works that I did in different parts of the cloud, I looked at what we can do. For example, for wired networks and middleboxes, I work on the Rosebud framework, which is for FPGA middleboxes that we double the performance of the state-of-the-art intrusion detection, which was Pegasus. And then in 3 weeks, we double the performance. And then we reduce develop time from months to days. For wireless networks, work on a framework for reducing the cost of wireless receivers. For example, we enable 10 times cost saving for software-defined radios, or enable 500 times cost saving for spectrum sensing. This was in 2019. And then in data centers, I worked for reducing the cost of compute. For example, how can, for scale-out applications, reduce the cost of making ASICs by being more wise? Or we were the first to develop a reliable cost model to actually know what is the cost. Or we enable 3 times cost saving for distributed machine learning jobs. So this type of work everywhere we can look at. And then there were even some adoption, for example, the work on wireless networks, already FutureSDR, software, hardware, many know that AmateurSDR or the Lawrence Livermore National Laboratory are using it, or we were doing the ML job with Meta. And then my approach personally is to find the unnecessary constraint, and based on that, gain this benefit. For example, for Rosebud, we simplify the development by adding negligible latency and area overhead, which was acceptable. For SparSDR, we reduced the backhaul and compute by adding latency and noise, again, within an acceptable margin. Or SweepSense, we did a full spectrum, but we don't get the full packets. AC clouds, going more wide about technology. So always there is something you can look into. Or on top of, we added again some latency. In this talk, I'm gonna focus on the first two, especially the FPGA seminar, which was based on FPGA, and then I will just very quickly go over the others. So let's start with Rosebud. So first of all, what is a middle box? So usually, if the answer to that question is, this is any compute that you want to do on network that routers and switches don't. So that means we need something which is very flexible. The example of it is deep packet inspection for intrusion detection systems, that if there is an intrusion, we want to look at the packet payload. And then the point is I have to process the packets payload byte by byte. For example, for attack signatures, it's not just looking at the headers. It's much more compute intensive. And then with the packet headers next to the payload, I can understand the context. And some, for example, here in the graph, you show in the picture that some of the packets are dropped, some of them can go through. The tricky part is we are talking about backbone internet. This is 100 to 400G and increasing data rates, and that means it has a tremendous amount of compute power. And then we always use CPU-based because we needed the flexibility. And the way we did it was we had some CPUs and a switch before them to distribute it among them. And then the point is this system is becoming very expensive. And actually, middleboxes are an ideal use case for FPGA acceleration. What we do is the packets come in, and then FPGA is the first one to look at them. And then the highest speed packets comes, and only send the exceptions to the CPU, something like the Pegasus paper did. And then on top of that, to this, FPGAs are tailored for accelerating CPU middleboxes. What I mean by that is we have some network targeted basic like logic. For example, for Ethernet MAC, it's already baked in. For PCIe or large buffers that I can use for networking, all of them are available. And then we have higher density FPGA, for example, multi-die, so there is more room for getting hybridization from them. Or techniques like partial reconfiguration that I can on the fly update. I don't have to stop my system and redo things. And then examples of this is CPU plus FPGA middleboxes is the biggest ideas that you're aware of. Does 100G and combines and goes into an accelerator. That being said, there are challenges. The fact that I wanna do line rate performance, it just exacerbates FPGA development pain. We need deep knowledge of FPGA features. The good things that I mentioned about, oh, we have Ethernet MAC, we have PCIe, and those, we have to know how to use them properly. We have partial configuration. It's just not something easily you can use. You have to know lots of constraints and restrictions. Another thing is we have a slow clock rate, 200 to 400 is the typical rate. And then this causes high logic utilization because I have to do lots of prioritization, and then placement becomes really challenging for that. Another point is we need very intricate orchestration of the accelerators. So we have heterogeneous accelerators as well as variable packet sizes. Different packet might need to go through different accelerators. That means an unpredictable time. It's not a simple streaming application. And then if I change one of my accelerators, that might break the orchestration logic. I have to redo the orchestration logic, which takes time. And finally, we need to debug hardware that processes millions of packets a second with very Byzantine debugging, because we have very, very limited runtime debugging capabilities. For example, with some ILAs, figure out where to trigger it. And then we have long development cycles, hours to just do simulation and placement and routing. That's why usually designing FPGAs takes a really long time. I'm sure people who are here and in FPGA design have to spend a lot of their time looking at waveform if the bug is in the simulation to figure exactly what happened. And then I was thinking, come on, my software middlebox was so easy to develop. I had Docker, Kubernetes, I could put breakpoints on FPGAs. I had kind of nothing. Milliseconds of waveform I can simulate. I don't have any runtime debugging logic, very little ILAs. And then let's say I make a debugging logic. There could be bugs in my debugger. I have to first debug those. I was like, can we do better? And then we came up with a new abstraction. We call it reconfigurable packet processing unit, or an RPU. Our idea was that with a familiar and effective abstraction for middlebox developers that they are used to in software, we can make network-targeted FPGA features that are abstracted away. For example, packets are accessed from the local memory as some DMA descriptors, the way that people wrote it for the CPU, or we can communicate with host again with DMA descriptors. That's an abstraction that people are used to. And then that way we can abstract away the complications of like PCIe modules, CMAC modules, and those. Another point is orchestration among hardware accelerators. We can kind of look at them as some, if we can make them as program like functions, that I do a function call. And then I do the orchestration in software. And now if I want to change a function, I can just update the accelerator through PR. So now the management, which was very intricate, was in software. And then the runtime debugging, again, I have a RISC-V core next to my accelerators. They have some shared memory. And then now I can use the software on those RISC-V cores, for example, to trigger a scenario when something is not going well, or even from the host, I can have a safe read back and load. So this abstraction is if I have a reconfigured packet processor, I have the core next to my accelerator, just a tiny core, and then a shared memory among them. I'll get into details. This is the high level. And we said with this abstraction, we can tackle these three problems. But you might be asked, come on, can such an abstraction really work at 200G, like a small RISC-V there? Our main insight is kind of reverse Amdahl's law. What Amdahl's law says, if there is a part of compute that is only taking 10% and you even improve it by 10 times, you are not gaining much. By reverse, I mean, let's say control. Usually for these data-heavy computations, they are taking like 1% of the time or even less. If I make that part a little bit longer, the hit on my performance would be very minimal. But now I can make things much easier. And then still, I have very wimpy RISC-V cores. They cannot do that much as well. For example, in this project, we run them at 250. And that's where we had to come up with a new architecture design to make the orchestration more efficient. For example, for data movement, we have some optimized DMA engines in the RPU interconnect. So next to each RPU, we put an RPU interconnect, and then on the data bus, I have some DMAs. So the core has to only handle these descriptors. It doesn't have to do the data processing inline. Another thing is for among different packets, if I want the software to do the processing, then it would add a lot of latency. But I can use hardware FIFOs, similar to OS queues. And then we work on a very sophisticated memory subsystem based on the needs of middleboxes to make this happen. On top of that, we added features that, for example, through host, you can dump the data or the state of the cores or load the instructions and so forth. As an example, I go to memory subsystem. So each of the RISC-V cores, if we want to use a large memory, the problem is I have to pipeline it, otherwise I cannot be timing. So it would add a lot of latency. A very small RISC-V that each cycle of load and store takes time would not be ideal. So what we did is we made a small memory for each of the RISC-V cores that can be accessed within one cycle. We have a large memory for packets to come, and also it can be used as a stretch pad, and then each of the accelerators have their local memory. Now, the way that we do things is that RPU interconnect, it can DMA data to the packet slots in the large memory. And because most of the time, the decisions that the RISC-V has to make is based on the packet header, not the packet data, we copy just the header to the local RISC-V memory. Now, for many types of applications, it can very quickly just access, okay, this is, for example, a TCP packet on this port. Do I need to run this accelerator or that accelerator? So I don't have to spend that much time just making the decision. And between the RISC-V and accelerators, we use some memory mapped I/O. And then by doing this, the packet data and the scratch pad is shared between accelerators and RISC-V. So if you wanna access something in the packet or add something, you can still do. On top of all of this, host can access memories for load and debug. So this is a unit at the heart of the Rosebud abstraction that makes this happen. Any questions, by the way? Okay. Still doing a few accelerators and a single RISC-V. Even it's doing control part, it's not that performant. And we're talking about 200G. But the point is, as I said, for CPU middle boxes, what we could do was, for example, use a switch to distribute them among some servers. So we can do the same here. So for example, if I put 16 RPUs for 200G, now each of my cores have to just control 2.5G. It's much more manageable. So what we did is we distribute the load through this replicating RPUs. So in the image, as you see on the right-hand side, we have some accelerators, RISC-V, and the memory inside each of those RPUs. I replicate them, and then on the other blue one that you see is a programmer load balancer that does the load balancing similar to procedure we had. And the rest of the system, the complications of PCIe, CMAC, or how to do a very efficient packet switching between them, we take care of those for you. So in the static design, we place them, so you don't have to think about that. So the first problem of how can I use those logic and then how to do this parallelization and host access, all of those are taken care of for you. Another thing is now we have coarse parallelism through workload-based load balancing. So we can even optimize how we want to load balance. And then, for example, here I'm getting already a 16x coarse parallelism. And finally, by doing the PR regions layout, we don't have to replace the full FPGA anymore. I can just update one of my PR regions or the PR regions, so it will make the debugging cycle faster. So we did build a full implementation of the Rosebud framework for popularizing FPGA. And then we made it open source. You can check it. I put the link at the end. And as an architect, I want to show you my goodies. So here's a layout, which also helps you kind of see where things and see how much Rosebud provides for you that you don't have to, as a middlebox developer, look into. So first of all, the PR regions that you can update, that we have 16 RPUs in this example, and then load balancer. So this is the only logic that the user needs to care about. The rest we do for them. These are the Ethernet MAC, and then the connection to the host. So that's how they're placed. This is the switching, messaging, debugging, for lots of debugging, for example, for runtime debugging, and all of those are taken care of. And just to give you a little bit more sense how it is connected, as we said, each interconnect, RPU interconnect is next to an RPU, and then those interconnect are connected to the switching system. So here I'm showing a few of the wires connected. And then here as an example, as you see, the amount of logic in those RPUs has increased. I'm using the same load balancer, just I added a firmware accelerator. So they are there. And then another idea is my number of RPUs can change based on the workload I have. So for example, if I use 8 RPUs, and this is the Pegasus, so as you see, the RPUs are rather on the fuller side. But the point is, as long as I'm within that boundary, especially for PR, you have to define a boundary. I can use those more efficiently and kind of based on the number of RPUs I have, decide how much. So then we did a performance analysis to see actually can we deliver. And as you see on the left-hand side, I'm showing the forwarding performance with just 100G port or 200G port. And the dotted line shows the maximum possible rate. And as you see, other than 64-byte packets, we can actually hit the full 100G and 200G with 16. So the delays that you get from the software, just reading the descriptor, sending out, is acceptable. And regarding the latency, we are again showing it from 64 to 9,000 byte packets. One thing that you see is between low load and high load, there is no difference. And the point is because my load balancer controls what goes through the network. So I don't have a congestion case. So the congestion is handled in the input buffer. After the load balancer, I have a state of each of my RPUs. I know, for example, are they keeping up or not? If not, I don't send extra workload towards them. Because of that, I don't see a performance difference between low load and high load. And regarding where is this latency generally coming from, actually the line that you see is the serialization latency. The point is because I have a 2-level switching system, the 100G coming in, but to each of the cores, for example, I'm sending up around 32G. So because of the serialization latency, one first at the MAC layer, and second to write to the core's memory and read out, that's the main part of the latency. And finally, at 64, you see suddenly under high load, there's a jump. There's no free lunch. So if you cannot keep up, your input RX FIFO gets full, and that's the latency that you're paying. But the point is, we are only doing it in the RX If we cannot keep up, we can be careful about what packets we drop. You have the control over your load balancer. But the point being, now over the course, everything got very nicely done. So for example, we have 16 slots, and then the cores talk to the load balancer, how much I can keep up with. So overall, I'm gonna say that we show that multiple RPUs help to amortize this software and delivery overhead. So let's go to some case studies and show does this framework really make life easier. So first of all, okay, I want to make a firewall. Let's see how long it takes. I took 1050 IP block list, and I made an accelerator to just match based on the IP. It was just literally a statement in Verilog, just within 2 stages. We could do it with HLS2, obviously. And then this is literally the C code I wrote for those risk files. So first, I have a pointer, my descriptor data. I just skip the MAC header and the initial part of the IP header, and okay, here's my source IP. Then I say that accelerator SparSDR IP is a register map location IO. I say put the value there. This is the C code, and then I read it the output. If I put the length to 0, my DMA engine would just drop the packet and take care of rest of the things in the system. And if I just export it, it will reverse the port. So it let it go by. And then I just say packet set. And we provide even the C libraries to do these calls for you. And with this less than a week, I could do 200 gigabit for any packet size, 256 bytes or more. And then we got to the more interesting test, which was the Pegasus. And then it took 3 weeks. To be honest, most of the time was spent because Pegasus was for Intel, and our system was Xilinx, so I had to convert some of the IPs which were Intel specific to Xilinx. And then within 3 weeks, we scaled it from 100G to 200G. Actually, one of the points was we could use URAMs because you cannot initialize them over bitstream, but now because of host access, we have write access to all of them. So we could use more efficient memories. And then also it's nice because of the PR part, we can update the IDS rules on the fly. And we did an interesting test. So here on the x-axis, you see different packet sizes, and then on the y-axis, the bandwidths. One option is just using a snort. This is of the CPU one on a 32-core machine. And you see, for example, the performance is at the bottom. The other option is to use the Rosebud hardware reorder, being that I do the reordering like Pegasus in my load balancer, and I only send ordered packets to each of the RPUs, and that achieves the higher performance. But we were like, okay, what if I want to do rapid prototyping? For example, I don't have that reorder engine written yet. What if I just use, I have 16 slots per core, but if I use a software code to see, oh, if the packet number of this speed, the sequence number is that, wait until the other packets arrive. I just wrote a little bit of C code, and as you see, around 1024 bytes, we already achieve 100G. So it means that it also enables that I try something in software to just prototype and say, okay, it's working. Now I have to go and make it to hardware. So that enables faster hardware iterations. So overall, with Rosebud, we achieved 200G on software running on some really wimpy cores. It's open source, and you can use it to make your 200G middlebox today. The code is available, and we got kind of artifact approvals from us. Any questions on this work? I'm gonna shift to software-defined radios. Okay. It's not good. So the idea is for SparSDR is they are coming to the base stations. Base station challenge is that it's really hard to update and add new protocols. For example, many of them you have to go on the top of the antenna to change a chip. That's why, for example, FPGA has become very popular there because doing ASIC and then every couple of months going up the ladder wasn't a good option. But at the end of the day, you have very few FPGAs per base station. How do you utilize them is important. And then there is a rising solution called software-defined radio. The idea being But if I capture the data and, for example, send it to a data center to do the processing, so the front end is over there, and then Cloud RAN for 5G is an example. And then the beauty is they are universal and flexible. They can decode any protocol on any band, Wi-Fi, Bluetooth, ZigBee, FM, LTE. And then there's no hardware development cost because hardware is only doing the capture. But the challenge is they have very high backhaul required. They have to send a lot of data, raw data, to the data center. That means a high TCO cost for the internet transit cost, and then compute in the data center. And then also even there is no available bandwidth for many base stations. So let me talk a little bit more about software-defined radios, how they achieve this and their pros and cons. So they get this flexibility by after an antenna, they have an analog to digital converter. That's the radio front end. Usually we have to do some downsampling, and then we send it to a CPU, a processor, or GPU, and then there we do filtering that I want a specific band, and I do the processing to get the actual data. But let me give you an example, a very commodity SDR, USRP2. It can actually capture at 100 megahertz, but it only has 1 gigabit per second backhaul link. So it has to downsample it by 4 times to make it 25 megahertz to fit within 800 megabit per second budget. And then we need a server class processor to keep up with 1 gigabit of data coming all the time. And then it's very inefficient when you think about it. Let's say I have a BLE. The data rate is 1 megabit per second, but now I have to process 1 gigabit per second to just do the decoding. And then we're like, is there a way to make this more efficient? So we did a measurement study that on the ISM band with one radio, they captured 125 megahertz for 45 seconds in some interval of 10 microseconds. And we saw in how many of them, we did the CDF, of there is actually any data, any signal going on. As you see, for about 40% of the time, there's nothing on the air. For about 90%, 80-something% of the time, we only need 512 megabit per second of backhaul to be able to send all the data. But all the time, we are sending 4 gigabit per second of data. Like, okay, can we benefit from this opportunity? For example, here, this is an example SDR capture that it's 125 megahertz and time is on the y-axis and frequency on the x-axis. And then it's showing me the energy of the signal. And I literally, by my eye, I could see the packet. Okay, here's the packet in yellow, and where it's blue, it means there's no signal, it's just noise. Can we kind of what we do with our eyes, put a threshold there, and then just get rid of the rest, and only backhaul and compute these active signals? That's what we call a sparsity proportional. That's why SparSDR. So we introduced the sparsity proportional backhaul and compute. So instead of doing the normal downsampling, we do a sparsity proportional downsampling. And then on the filter, again, we do a sparsity proportional to make the system based on the amount of data on there, not based on the worst case scenario. And then beauty is the front end fits in existing FPGAs. You didn't have to buy any new equipment. And then on the back end, we could even run it on an embedded processor. As an example, we did a Raspberry Pi to handle 100 megahertz of bandwidth, which previously needed 3.2 gigabit per second of bandwidth. And then just using a very commodity end-to-end. How do we do this? A little bit of signal processing part. So we capture the signal by SDR front end. Then we divide the signal into discrete intervals. And then we perform a FFT, discrete Fourier transform, to go to the frequency domain. One point is we send our signals in different bands already. So if I go to the frequency domain, I can see my signals there. Then I do the throwaway threshold of the pins that are not used, and I only backhaul what's left. This is the high level of how SparSDR works. Very simple, very based on math. And then some detail for signal processing folks that you had to do some overlapping hanging windows to focus the energy, but that was about it. So a little bit of signal processing to make sure we are not spreading among extra pins, and then that was any questions.
You have situations, I think there might be some technologies where the energy is well below the noise floor, so it might not pop up when you do the FFT.
Right.
So are there certain kinds of technologies that you can do this for and certain kinds that you cannot?
So that's the thing that I said, the constraint that we let go. One of them was like, for example, if I do a 2048, I get 20 dB gain, but if it's below 20 dB noise floor, then I would use this.
So you think the SNR has to be 20 dB or above? Is that
Because, so I get 20 dB from doing 248 FFT, but if it's like more than 20 dB below the noise level, I cannot start. Yeah, but so that's the thing. For many applications, we didn't need that. Like, okay, for them, we can benefit from this. But yes, if it's below, like, I forgot the name. What is the word that also was doing? Forgot the name that they are focusing on the signals well below the noise floor. For example, they did it on their farm project.
Okay, farm beats you mean?
Yeah, farm beats project.
Yes.
And then for them, it's not gonna work. So this was kind of the front of the system, and then now it's time for the backend. So for reconstructing the signals on the backend, the naive method would to be, okay, I did a Fourier transform on the front end, I have to do a reverse Fourier transform on the back end. And then, so I get the frequency domain data, I fill the rest with zeros and do a full IFFT. And then, like before, I do filtering to select a specific band and get a time domain signal. The problem is it's not sparsely proportional anymore. Again, I'll have to do this compute based on the full size Fourier. What we can do instead is to do partial IFFT. So when I see my signal is, for example, only 32 bins, I can bring that to the center frequency and then only look at that, take a IFFT as only those many bins, and already while I'm in the time domain, done. We had to do some lightweight phase correction, the part I say I just bring it, but it's very lightweight, just multiplied by some constant factors. So we did a case study of a universal IoT gateway that I use a USRP N210, which is a very complicated device, and a Raspberry Pi 3, and then we reconstruct and decode Bluetooth captures in real time on Raspberry Pi. And then our main question was, is SparSDR really sparsely proportional? Does it deliver? And then, so here is a 100 megahertz capture on Raspberry Pi. It's not a beefy server. On x-axis, we are increasing the advertising rate. I think how many packets are we emitting to be captured by SDR. And then on the right hand, you are saying the data rate, the received data rate after SparSDR. And as you see, data rate is almost linear. So the more packets I send, the more backhaul I receive. And then if I look at the CPU usage on the left-hand side, again, the 4 cores are on Raspberry Pi, they're almost linear. So both our front end and back end are linear. It was nice to see some impact. Some developers started to use this, which was nice, like Future SDR or Bastien already put this video online that, hey, I'm using a SparSDR and I can capture things in real time quick and nice. Or we have some collaboration with Lawrence Livermore. One other thing which was cool, my colleagues at UCSD, they wanted to do some BLE location tracking attacks and show that you can see a lot of information if you wanna hack people. And they wanted to capture for a week or two the data at some location that there was no even Wi-Fi signal available. So they put a small SparSDR unit literally in the cake box with a small SSD next to it and put it there for 2 weeks. They capture all the data, nothing happened, it worked for 2 weeks, and they use that data to do the analysis. So the fact that now I have to process much less data and save much data was very useful for them. After the paper was out, we added support for Bluetooth SDR, which is only $200. You can just go and buy it and try it. And then even we made the system more efficient by up to 2 times less backhaul. And for folks who do SparSDR, SDR stuff, it's radio compatible. So now I'm gonna briefly go over my other frameworks very briefly and see, for example, other things that we can benefit from customization. So in sweep sense, still we were using SDRs. The idea is I can now sense 5 gigahertz in 5 milliseconds with low-cost SDRs. So if you wanna do that nowadays, for example, some agencies have to do this. What they do is they have a very wide band spectrum. They capture all of it with lots of the small SDRs or fancy software device, and they have to capture all of this, and they become very, very expensive. But at the end of the day, we said we only need to know if there is a packet and what is the type of the packet. I don't need the actual data. So what if I sweep the frequency domain super fast, just sweep, sweep, sweep. Even if I get a glimpse of the packet, I know there was a packet. And then we came up with some novel algorithms to classify the packet from just that partial capture data. And now, again, with some N210, something super cheap, like $1,000, we could do something which is $500,000. Another work I worked on was ASIC clouds. This is more ASIC, but it could have been FPGAs too, that we can benefit from ASICs for planet scale applications. The idea was we developed a flow that from an accelerator properties, that for example, what is the performance, what is the power budget, and so on. We put them within an ASIC, we add the other things you need for an ASIC, like power grid, PLL, and think about those. And then how many of them we can put on a server. Then we have the cooling issues. Can I cool this system or not? Or we came up with some novel ideas how to do this. And then we consider DC-DC converter, costs, oscillators, and all of those. And then put this in a rack, and then put these racks in a machine room. So all the way from accelerator to a complete data center. And then how can we find TCO optimal? TCO optimal is not the one which is the most performant or the most energy efficient. Based on factors like what is the cost of electricity in your region, that would be different. And then, for example, one thing is the Google's video cloud is example of that, or we saw Bitcoin or Litecoin before. And then we did the first NRE model. And then we can potentially do similarly for FPGAs, but this work was, for example, for ASICs, or the fact that instead of going to like 3 nanometer now, what if I do something in 14 nanometers? It will be much cheaper, and the performance improvement I get for some applications are not that great. It's not worth it, or if I want to start. This insight help us to, for example, how can I make an ASIC cloud with less amount of money? For example, back then in 2016, we showed that you need 1 billion demand for 16 nanometer to make sense because of the mass cost and upfront costs. In the two-part work, we did some co-design between application and network topology. The idea is we did some captures from Meta that different workloads, machine learning workloads, have very different traffic patterns. And then if we have to make one design, for example, the factory, which is typical for all of them, we have to over-provision a lot. What if I tailor my network to my prioritization strategy and together optimize? And then we came up with some, for example, ideas like ring reduced permutations to increase direct connectivity among the nodes. And then, for example, among some nodes we have rings, and among some nodes we have auto-all patterns. And then by doing this co-optimization, we made the traffic pattern to be much more uniform. So there's not some links super underutilized, some links super overutilized. And then we didn't just make it in simulation, we actually implemented it at MIT. We had the 12 A100 servers and then an actual patch panel. And then, for example, one cute idea we came up with is the one problem with patch panels or optical switches is that they take a long time, in order of milliseconds, to change who is connected to who. but we came with the idea of kind of like double buffering, that we have some tiny switches next to each NIC, that all of them are now have 2 ports from each of the ports of the NIC. So while I'm doing a training of one job, I can plan for my next training. And when I wanna just switch, I have to just do one 15-millisecond change. And then when I have jobs that run minutes to hours, if 17 milliseconds is nothing. But then I could lower the cost of my system. I didn't have to switches, lots of transceivers, lots of fibers among them. So I could lower the system cost, but almost 3x at the same performance. This was a work we did with Meta. I'm not sure if they are still continuing doing that. Lots of things changed in Meta, but it was like, I'm going to talk a little bit about FutureWorks, and I open the stage for questions. One thing is, for example, the Rosebud paper. In the paper already it was dense. We didn't talk about new features, but right now we have said that all of the RPUs are the same. We just scale them out, but there is no constraint. You can put different RPUs which have control over what goes where. Or another thing is, we wanted to add HBM support. Actually, at the time of the paper, the Xilinx IP for HBM wasn't good enough. So we gave up, but right now, for example, they have better FPGAs, that they have nice HBM, for example, for each of the clusters with 4 RPUs, you can allocate 1 HBM or use their logic to share the memory among them, which would bring more local memory with high bandwidth for state sharing. And then even kind of my vision is the RPU can become like a library, that, okay, these boards are supported, for example, 8 RPU and 16 RPU designs, and I can get somebody else's RPU and just place there. So during runtime, I can literally just load that. I don't have to do any FPGA development per se. Look at it as a function. And then we can have some disaggregated and serverless computing for FPGAs. If we do some integration with Rosebud, that, for example, one simple example is we have different RPUs. I can allocate them to different users or allocate different functionalities at different times. And by that, do a virtualization. For low-cost SDRs, we can have some security research using low-cost wireless sniffers and spectrum monitors, because people abuse the system. It's good to at least get a sense of what are the signals out here. And then actually there was a paper from our team that it was law enforcers about the pump stations, the gas stations, and they could figure where there is the scammers. And then we can have a unified gateway for IoT devices and in 5G networks again, using then the way I see it is that 5G can become some protocols as a library for SparSDR. Or things that we can do is, let's say you have a cell phone. Still, the backhaul is now so much less that you can send it over to 4G or 5G. And then the work that I personally am doing still is more on the ML and HPC applications at Nvidia, and then adding and improving the network features with application needs in mind. And then you can look at those GitHubs, they're open source. I'll be happy to collaborate on those in my free time. So with that, that's my talk.